before the class. So here I am today to make you a video that I'd like you to watch before you arrive. And then when you are here with us at Iron Range Engineering, we will take this learning one step further. So one of the competencies that all engineers learn is fluid mechanics. And fluid mechanics has 5 real basic fundamental principles. And today we're going to dig into 2 of those. One is called the energy principle, and the other is called the continuity principle. Now, you've experienced the energy principle before because it comes from the law of conservation of energy, which is learned in physics, it's learned in dynamics, and we just have its own application here in fluids. And then the continuity principle is very much like conservation of energy, except it's conservation of mass. And we're going to use both of these principles in our problem. Now, what we're going to do is we're going to have our problem be a tank of water. And in our tank of water, we are going to poke a hole in the side. So the water, once we poke the hole in the side, will go flowing out. And the ultimate question that we would like to be able to answer, because it has a lot of applications in engineering, is how long does it take for the tank to empty? Time to empty. Now, what's causing the water to flow out here is the pressure due to the height of the fluid in the tank. And so as the height comes down, the pressure pushing the water out is going to be less, and so the flow out of the tank will be less. So this isn't a simple 1 equation, 1 unknown, or 2 equations, 2 unknowns. It's much more complicated than that. The solution is actually the solution to a differential equation. But we're going to use more of a finite element analysis, a finite element approach to finding out how long it takes to empty the tank. And we're going to predict this using equations in class. And then you're going to go and build one of these in our lab and predict for the one you build how long it should take to empty. Then you're going to run the experiment and see how long it takes to empty and see how close your prediction was to your actual. That building something and testing it, some people refer to that as like hands-on learning. At IRE, we refer to that as a deep learning activity. And you'll hear us use lots of acronyms. We call this one the DLA. So back to the problem at hand here. The energy principle allows us to pick 2 points in a fluid. Let's call this point 1 and this point 2, and write an equation for the energy on one side, and energy comes in 3 forms: the pressure, the height, where height is this dimension, and the velocity. So the pressure at point 1 divided by its specific weight, the height at point 1, the velocity at point 1 squared divided by 2g, minus the head loss, which is a frictional loss right where the water exits the tank, equals the pressure at point 2 over the specific weight plus the height at point 2 plus the velocity at point 2 over 2, and g is the acceleration due to gravity. So that's the energy principle. And the continuity principle allows us to calculate the flow rate at point 2. So the symbol that we use for volume flow rate is a V with a squiggle, that's volume, and a dot, that's rate. So we know what a gallon of water is, and flow rate is measured in gallons per minute or cubic feet per second. The equation for the volumetric flow rate, and this is the continuity principle, is equal to the area of the hole. So like if I could get the diameter of that hole and calculate the area using pi r squared times the velocity. And so the volumetric flow rate at point 2 is equal to the area of the hole of point 2 times the velocity at point 2. When we do this problem, there are going to be some simplifications we can make. The pressure felt at point 1 is atmospheric pressure, and that's the same as the pressure at point 2. So the pressure at point 1 and the pressure at point 2 are the same. The height at point 1 is the thing we can measure, and we are going to, at least on our first go-around, neglect the friction, call it approximately 0. And if we say that the height is equal to 0 at the hole, then when we measure, we can get the height at 1, so we can call the height at 0.20. And it turns out that by the continuity principle, however much volume is flowing down, that's the same volume that's flowing out. Now, so the volumetric flow rate at 1, which is equal to the area at 1 times the velocity at 1, is equal to the volumetric flow rate at 2, which, as we said, is the area at 2 times the velocity at 2. So we can simplify this equation to say volumetric flow rate at 2 equals area at 2 equals volumetric flow rate at 1, area 1 times velocity 1. We can just call all of that volumetric flow rate. So I'm going to rewrite the energy equation. As the height at 1 that we can measure, plus the volumetric flow rate over the area at 1, that's velocity, squared over 2g, equals, oops, we got rid of that. All that's left is the velocity at 2, which is the volumetric flow rate over the area at 2 squared over 2g. So now what we've done is what's the word I'm looking for? Combined the energy principle and the continuity principle to get one equation where there's a height that we can measure, an area that we can measure, 2 and gravity, area we can measure, 2 and gravity. So the only thing we don't know in this equation is the volume flow rate. So we can predict for any height, we can predict how many gallons per minute are going to flow out. Let me hop over to a new page here, and we will solve that equation. Height at 1 plus volumetric flow rate squared over area 2 squared 2g, area 1 squared equals volumetric flow rate squared over area 2 squared and 2g. I'm going to solve this for volumetric flow rate. I'm going to say volumetric flow rate squared times 1 over area 2 squared minus 1 over area 1 squared equals Z1. So basically what I did is I moved this to the other side of the equation and then simplified it out. So now I can say volumetric flow rate squared equals Z1 times 2g divided by 1 over area 2 squared minus 1 over area 1 squared and if I want to get rid of this square, I can take the square root of everything, and everything in here I can measure. I can measure the area of the tank, I can measure the area of the hole, area of the hole, area of the tank. I can measure how high the water is, Z1, and I can measure 2, which isn't measurement, and G, which isn't a measurement. So at any height, I can calculate what the volume flow rate out of the hole is. So if we've got that big tank, and we've got water flowing out the side, and I then decide to take the tank, I don't like that color. There we go. Seriously, I don't want that color, I want this color. There we go. And I take maybe each inch of the tank. Let's say that the tank is 60 inches tall or 40 inches tall, and I break it up into each inch. For each inch, I know Z. So then I can calculate the volume flow rate. Now, volume flow rate is equal to the volume that flows out divided by the time that it takes to flow out. So the Z gives us the volume flow rate. Let me just rearrange that for time. The time it takes would equal the volume divided by the volume flow rate. So in other words, the time that it takes to drop 1 inch would be the volume of 1 inch, which we can get because it's just a cylinder, divided by the volume flow rate, which we can get from the equation on the previous page. And now we can predict how long it takes to drop this inch. And then we could predict how long it takes to drop the next inch. And then we could predict how long it takes to drop the next inch and the next inch. And if this thing were some number of inches tall, let's say 37 inches tall, we could predict how long it takes to drop each of those 37 inches, add them all up, and we would now predict how long it takes to empty the tank. So, the whole purpose of this conversation here was to tell you that we've got this thing called the energy principle. We've got this thing called the continuity principle. We can combine them together to predict